Do you remember what these particles are and what their purpose is? You already know that we're made of cells. Cells of molecules, molecules of atoms, an atom of electron shells, and a small nucleus in the center. A nucleus of protons and neutrons. And this is where school physics ends. But we need to go further, deeper. So, protons and neutrons are made up of quarks glued together by gluons. Those 69 kilograms inside me from the beginning of the video are the gluon springs that glue the 700 grams of my quarks together. They're the elements of the Standard Model. Nowadays, all matter, absolutely everything, is made up only of these particles. Neutrinos are formed in the sun, but the rest, the bottom, strange, charm quarks, muons, and taus, used to be a matter only at the origin of the universe. They don't exist now, but they can be obtained in colliders. Here are bosons. These particles determine how matters interact with each other. They work like messengers, bouncing between the fermions and telling them what to do with each other. The gluon is responsible for the strong interaction, the most powerful force in nature. It glues quarks within protons and neutrons. The photon mediates the electromagnetic interaction. These are radio waves, visible light of all colors, radiation, and the repulsive force between molecules. W boson and Z boson mediate the weak nuclear force. They're responsible for radioactive decay and thermonuclear reactions, for example in the center of the sun. And here's the particle that bonds everything else together, the Higgs boson. One particle to rule the others. What would it look like? Imagine a ball, like at school. Ready? Forget about it. Fermions, bosons, and other elementary particles can't be imagined, can't be smelled, can't be touched, can't be seen, can't be felt. It's magic, which can be explained only in the language of mathematical equations. Okay, that makes sense, right? Back to the Standard Model. It's not so simple and has a reverse side. Each of these particles has an evil twin. Antimatter particles. They have no difference except for the sign of the charge. The electron has a positively charged electron, known as the positron. The proton has an antiproton, and hydrogen has an antihydrogen. When colliding with the matter, they mutually annihilate, releasing energy. Antimatter can be found in space, or produced here in the antimatter factory. It's the most expensive substance ever known to humankind. Antiprotons fly in here at almost the speed of light, really fast. But it's impossible to research them all at once. It's like spotting a train number at full speed. Impossible. Hence, the antiprotons must be decelerated. It's done here, in these decelerators. Every time the proton flies through them, it loses energy, and eventually slows down 1,000 times, until it finally gets into a magnetic trap where it can be stored for years. Here, powerful magnets repel antimatter particles from the walls. It's like the ghost trap in the Ghostbusters movie. It prevents antimatter from interacting with ordinary matter. Yeah, antimatter is dangerous in large quantities. 2 pounds of antimatter coupled with matter can make an explosion with the power of 1,000 atomic bombs dropped on Hiroshima. It would be an absolutely pure explosion. No radiation, no waste, just an explosion. For antihumans, who would be made of antimatter, we would be antihumans. That's why Richard Feynman once said, if you hold out your right hand to a man, and he holds out the left one, run away, because you might explode. Well, I realize that it sounds just like a new season of Rick and Morty. An absurd, confusing reality, but that's the reality. The quantum reality in which we live. The Higgs boson is the last piece of the puzzle called the Standard Model. Its mass answers the question, is there anything left to be discovered beyond this table? And most importantly, what universe are we living in? If it turns out to be light, 115 GeV, then the supersymmetry theory, or SUSY as scientists call it, is true. Supersymmetry is not the usual right-left symmetry. Supersymmetry is the symmetry of matter and interaction. In the supersymmetric world, everything is once again turned upside down. Each particle of the Standard Model gets a supersymmetric partner, photino for photon, squark for quark, Higgsino for Higgs boson, and so on. Their functions change completely. In our casual world, fermions are bricks and bosons are builders arranging them, while in the supersymmetric world, and vice versa, bricks would arrange builders. Supersymmetry is a cherished dream. But why? It might solve a huge iceberg of problems. One of them is this: why are some particles in the standard model billions of times heavier than others? It's like comparing the mass of a mosquito and a Boeing 747. That's how great the difference is. Supersymmetry solves this problem. But if the Higgs boson is heavier than 140 GeV, then another theory is true. It says that our world is not unique, and we live in a multiverse. That is, there are many universes, and anything can happen in each one. Multiverse? Sounds cool, yeah? Here's what Stephen Hawking said about it. Somewhere out there, Hillary Clinton is president, and I'm the world record holder in the marathon. Great! Huh? But for scientists, it's a defeat. Since they've spent hundreds of years trying to learn the universal laws of nature and find the answers to all the questions. Who are we? What are we made of? And where do we live? But if there are many universes, then we live in a random world of 10 to the power of 10 to the power of 10 to the power of 7 others? That's a lot, and the Big Bang Theory is just a puff in a world of other puffs. So which of the two theories is true? What kind of world do we live in? It was defined here, on the 4th of July 2012. It was the most important event for elementary particle physics, the discovery of the Higgs boson and the announcement of its mass. Physicists queued throughout the night, just like for a new iPhone. The answer to the question of what universe we live in depends on one thing. How much does the Higgs boson weigh? And does it even exist? Finally, at 9 a.m. local time, the conference began. Scientists spent a long time showing each other charts, diagrams, and bright drawings that made my eyes water. But the most interesting were these charts. One axis shows the number of events, and the other shows their energy. The curves are straight, except for one place, 125 GeV. So, the particles are there. Higgs boson, the one sought by scientists. The chance that they were wrong? 1 in 3.5 million. While everyone was shaking hands, a man was crying right in this seat. This elderly man is Peter Higgs. He's crying because he never expected to experience this moment. The theory he created 50 years ago turned out to be true. A year later, he received the Nobel Prize in Physics. The most significant physics event of the 21st century has left scientists puzzled. 125 GeV? Really? We were expecting heads or tails, but the coin fell off the edge. That is, the result is in the middle. The weight of the Higgs boson is 125 GeV. If there is a God, creator, whatever, then he carefully hides the truth from us, leaving only clues. He seems to play hide and seek with us at the point when we're about to get close to the truth. He adds another challenge, as if saying, "Wow, guys, you're good, but not this time." We are the same Homo sapiens as 100,000 years ago. The same brain size, and the same physical capabilities. What makes us different is the time we live in and the culture. That's it. Whereas science used to progress in small steps, and now it's moving at the speed of a truck. But perhaps, quite soon we'll hit a wall and won't be discovering any new particles. Maybe we've reached the great desert of physics, where we can't discover anything else, and that's the limit. There are no other particles. Even if we build a huge accelerator around the black hole in the center of our galaxy, we won't discover anything new. While skeptics were writing their articles, CERN was working on an upgrade of the Large Hadron Collider. It's begun accelerating and smashing particles in 2021. Now, it works at higher energies and with more accurate detectors, the data from which is processed by artificial intelligence. This means that we're back in pursuit of answers of the most important questions in the universe. Anticipating the skeptics in the comments, I want to answer the question, how can the Higgs boson be useful to humankind right away? I'll quote Frederick Bourdry's thoughts on the subject. There is an electron, and there is electronics. People knew what electronics were, but they didn't know about the electron. Now, we have boson, and soon there may be bosonics. So far, our minds are incapable of figuring out how to use the Higgs field to our advantage. But sooner or later, we'll figure it out. Maybe we can learn how to disable mass, and then any matter will behave as it did after the Thanos snap in the Avengers. Look, he disabled the mass of Spider-Man's quarks. This could be used as a weapon. For example, to stop a comet flying toward the Earth by turning off the Higgs field for it. Its gluon bonds won't be able to hold the particles, and it will disintegrate. That's all there was to tell. So, I did. One more thing. Everything that's happening here at CERN is done for the first time. These machines have neither commercial nor military potential. Considering the economic value, it's a waste of money. But for scientists, the collider is priceless. After all, it helps answer the most childish questions. Who are we? What is the world made of? How did it begin? And how will it end? And, as always, pump up your brain. Bye.